So, welcome back, students. So, this is the week 3 interactive session on traffic engineering. So, as we did in earlier 2 weeks, we shall first we shall start with the topics that has been already covered in this week 3 module. So, basically, I will give you a brief refresher about what are the topics that already had been covered, and then we shall come to our actual question answer session. And because this week 3 is about shockwave and queuing, so there are multiple numericals are also involved, and also it is I present some of the numericals for you in this module, and I hope that these numericals actually help you to solve the numerical problems in your assignments as well as in your final exams. So what we see generally that people are not getting that much of marks in the final examination especially. So I hope that by discussing here some of the potential questions that may come in the exam, so it will help you to solve it smoothly in the exams, right? And also develop better understanding regarding this, right? So maybe we shall start the session. So these are the topic that has been covered. So we can start with the shock wave, right? So this is a module of shockwave and queuing, right? So first 3 lectures is on shockwave, and then the I think rest 2 lectures or last 2 lectures are on queuing, right? So what is a shockwave? So basically shockwave is the demarcation between two flow state conditions, right? So we have already talked about what is a traffic stream and what are the traffic stream parameters, right? So if you see what are this is the traffic stream. So here we have 3 parameters: traffic flow, then the speed of the traffic stream, right? And then the density of the traffic stream. So these are the macroscopic fundamental parameters. So if there are two different flow states A and B, and it may indicate any one of these 3 conditions. So suppose flow at A is different than flow at B, subsequently it will impact your speed and density as well, right? So in that case, whenever your state changes from A to B, so there is a demarcation, right? So that demarcation point, we can call it as a shock wave. So why it is a wave and why it is a shock? Shock means, suppose we can look at it using an example, right? So suppose there is a signal intersection, it is red right now, it is green, right? Green and red. So now vehicles are passing whenever it is green, right? So now suddenly it is become red, so vehicles are suddenly stopping and queuing, right? At the upstream of this signal, right? So that means the flow state was something else, so flow density, those are something else previously. So now suddenly it stuck, so there is a shock, right? And why it is a wave? Because continuously it can move either this side or that side, right? Sometimes also it may fix also, right? So it's a kind of wave of vehicles, and how they are moving in a platoon, those things. So that's why it's called a shock wave, right? So now we can also we will discuss it that how these things actually are calculated in later on. So if we see, there are mainly 2 types of shock waves, right? So there is a 2 types, not maybe there are 2 ways that we can analyze shock waves. So one is the qualitative analysis, right? So then second one is the quantitative analysis. So quantitative analysis we will come it later, right? So first let's look at this qualitative analysis. So in case of qualitative analysis, basically it tries to tell you what are the kinds of shock waves that are created at different scenarios, right? So suppose let's take an example of a signalized intersection, right? So if there is a signalized intersection, so how many kinds of shock wave can be created, right? So suppose this is a red signal, as I have told. This is a signal. So now green, suppose this state is A, flow state. Flow state means flow speed density. That state is A. So now during green it is A and no shock wave is created. Suppose the demand is constant, like whatever the number of flow, number of vehicles are coming, so it is throughout same, and also you can assume that the width is also same, width of the road. It is also not varying spatially, right? So at that scenario the flow state is A, it is remain constant, so there is no shock wave, right? So now as soon as it is red, so now you see there will be some vehicles which already passed through the intersections, right? And here there will be many vehicles which will queue, stop, and this kind of queuing will occur, right? And here from the far away distance the vehicles are also coming at a rate of A at this flow state, right? So now you see, what is shock wave? Shock wave is the differentiation between two, or demarcation between two different flow conditions, right? So now as soon as it is red, so immediately downstream of that signal, so there is no vehicles, right? And here there are many vehicles, right? At least there are 2 or 3 vehicles depending on the width of the road, and then it is queuing. So at this point there is a shock wave, and is it that shock wave is changing its position? No, it is the same line because the vehicles are fixed, 3 vehicles. And here what is the density and flow, and here almost there are some density, it may reach to jam density as well. So suppose it is kj, and here what is the density? 0. What is the flow? 0. Everything is 0. So there is a change of state, right? So it is called the frontal stationary shock wave. Frontal stationary. Why it is frontal? It is at the front end of the congested region. Which is the congested region? Congested region is this. This region is the congested region. It is called the frontal stationary shock wave. Stationary means it is not changing its position. So now you see, so like this the queues are forming, right? So now as these vehicles more and more are joining towards the end, and you see your this is changing. So first it was there, now your shock wave is there, then your shock wave is there, now your shock wave is there, now there, right? And it is between A, what is the previous, and the newly, suppose if it is, we can call it as a B. So then between A, B, the shock wave is backward moving, at least that we know, right? It is moving, it is moving at the backward side, right? Not in the direction of flow, but the opposite to the direction of flow. So it is called the backward moving. So now is it forming or is it recovering? So actually you see, as the shock wave propagates, it propagates backwards, the congested region is forming, right? It is forming. So as it is forming, so we can say that it's a backward forming shock wave, right? So now we found 2 shock waves. One is frontal stationary, another is backward forming. Now what about this? So you see, here is a state where is 0 flow, 0 density, right? So now here is a state, there are some vehicles which are constantly going here. So as it is going front and front, the shock wave also changing its positions, right? Obviously. So then it is forward because it is going to the same direction, so it is forward, and it is also moving. But now the question is it forming or is it recovery? So actually it is recovery, because as the shockwave is propagating forward, uh, in the forward direction, so there are less and less and less vehicles are there, right? So they are dispersing of vehicles. So it is not that as the shockwave is propagating, there are more number of vehicles. So here what happens? It is stacking up the number of vehicles. So here it is dispersing the number of vehicles, right? So that's why it is called the forward recovery shockwave. So now there are three shockwave whenever the red signal arrives. Now what about after red? So after red signal, or after the red it turns to green, what happens? Suddenly your D state vanishes, right? Immediately there is no D state. So now, and also your B state is changes to some, suppose C state, right? And your D state is changed, means D state is there, but it is, as it is going, there is some different states, right? So now there is a shock wave which is called C, because now new state is C and your congested state was B. So BC there is a state, and C we can assume that C is a state where maybe saturation flow. At saturation flow, what is the state that you can call C, because as soon as your signal turns green, vehicles will try to flow or try to flow uh, at saturation flow, right? So basically now if you imagine there is a stack of vehicles are there, and now if they are moving forward, so the shock wave is, as it is moving forward, suppose as it is moving forward, so now shock wave is going to the backward direction, right, for the dissipation of Q. So that's why it is called the backward but recovery. Why it is recovery? Because the Qs are now releasing, we are releasing the Q. So it is called the backward recovery shock wave, because we are releasing the Q, right? So now what happens after we release all the Qs? So there was previous state was A, now the state was B and C. C is the that state, but then there is a new shock wave called the AC. What is it is? It is obviously forward moving, because it is moving in the forward direction, right? So it is forward moving, and also it is forming, because now A is relatively lighter flow and C is saturation flow. So as your vehicle is going closer, as your shock wave is propagating, so it is try to create congested zones. So it is forming, right? So now, so if I remove these things, because these are one only slide and it looks messy also, so it may not be difficult for you to understand. So so let me erase all of this information. So we already know that during red time, so there were three shock waves, and during red time one is the recovery and one is the after dissipation. But as soon as it is turns green, so there is also something called C and D, right? D is zero flow, zero, that situation, and C is what? C is at saturation. So between them also there is a shock wave. So is it forward moving? Yes, it is forward moving. Is it forming or recovery? Actually it is also what? It is also it is not recovery, it is forming actually, because now there are vehicles and it is going, no, it is actually recovery, because it is going to this direction and it will recover, right? No, it is forming, sorry, it will be forming only. So basically these are the concept. One is your shock wave is moving or it is stationary. So this is one point. Another point is it forward moving or backward moving? Back, right? And the third is it forming? Is it that the due to the propagation the congestion is forming, or we are releasing the Q? So based on that, forming or recovery, right? So this actually brings us to this qualitative analysis. What are the kind of shock wave that may present, right? So now also there was another example where actually it's a slightly different example. It was based on this one bridge is there, which is a bottleneck. Basically, a bridge has the less capacity than the adjoining roads, and then the demand is also varying. Here we assume that demand is not varying. Here also, if the demand is varying, so it actually complicates our scenario as well, right? Because A is not fixed, then A is constantly changing, right? So then in this scenario, what happens? So demand is increasing and then it will again decreasing, right? So suppose this is the peak hour demand, so it is increasing and then it is actually goes back to the same value. So for that actually I am not going into the details, but I am just saying a few things, how many types of. So there actually you will find another type of shock wave which you have not found in case of signalized intersection, which is called the rear stationary shock wave. So why it is rear? So if you know the frontal, it is at the front end or the downstream end of the congested region. And if you have some shock wave which is generated at the back, right here, so it is also called the rear stationary. So when it happens, whenever your demand has been increased and then it is decreased to the capacity value. So suppose it is the 3-lane road and it is the 2-lane bridge. So now your demand is first 2 lanes, then increase to suppose 2.5 lanes, right? So whenever your demand is increased to 2.5 lanes, because there is a 2, so maximum this many number of vehicles. So here you will see a backward moving shock wave, right? Vehicles will stack. So as vehicles are stacked, and then if you find that the demand again decreases to 2 lanes, suppose, so then what happens here? One shock wave will be created, which is the constant shock wave, because now the maximum, because your demand is 2, your here capacity is 2, and your already shock wave is created and your queuing is also 2, right? So one rear stationary shock wave is also will be created. So that's what here actually it is written, shock wave at signalized intersection based on the qualitative criteria and also the lane drop. Lane drop means at a bridge generally we generally suppose we are connecting, maybe in most cases maybe for a bridge there could be reduction in capacity. So it's a real life example you could say, because generally for bridge it may be expensive to build it exactly equal to the what is the adjoining roads. It may be, sometimes it may not be the case, but sometimes it also may be the case. So now in case of quantitative, so what do you mean by quantitative? So now we want to quantify the shock wave. So what do you mean by quantify the shock wave? So as I told, the shock wave may be stationary or it may be moving, right? Either in the forward direction or maybe in the backward direction. So now quantitative analysis refers to the rate at which it moves. So it is, suppose we are saying it is moving, then what is the rate at which it is moving? Rate means the speed, right? So whenever it is stationary means the velocity is zero, right? But whenever it is suppose moving in the forward direction, it has some velocity, right? So what is that velocity? And that if you imagine the number of, suppose in case of a red signal at signalized intersection, right? So during red time what happens? Backward forming shock wave actually created, right, at the upstream of the stop line. So now if you imagine what can happen, as your shock wave is going to the direction, so there is a speed at which it is moving, and it actually depends on the, in case, because one part is fixed, the vehicles, and then it depends on the speed at which the vehicle at flow state A are coming or the demand is coming, right? So now we are not going to the uh, discussion on quantitative analysis, since it is already there in your course material as well as in the video or lectures, right? But what we want to see here is that the final formula is q if speed of the shock wave is suppose s, so it is basically qa qp minus ka and kb. So if you see, this is the qk curve, right? So suppose this means what? So a lower density and higher flow is meeting to a higher density and lower flow, because this is q1 and this is q2 and this is k1 and this is k2, right? Or ka kp. So now if these are the scenario, so what is the shock wave of the speed of the shock wave? So q by k is equal to speed only, right? So if you do like this, and derivation I think is given in the actual course material, right? So this is the speed of the shock wave. So now in case of signal, you want to calculate the speed of the shock wave at each, like if you remember how many shock waves are there that time, there are 6 shock waves are there, 3 during the red, and then during the green initially there are 2, and then after the complete q dissipation there will be one new shock wave, right? So there are 6 shock wave at signalized intersection. So for each of those shock waves, so there is a speed, right? So then you have to calculate that speed at for each of these shock waves. So now temporary speed reduction at a section of highway. So we did not discuss in whenever we are discussing the qualitative analysis. So for this case, so suppose one truck is, suppose this is the highway stretch. This is the highway stretch. So now suppose vehicles are traveling at a flow state A. At a flow state A means at a certain Q, at a certain K, or at a certain V, right? Means at a certain flow, certain density, as well as at a certain speed it is traveling. So suppose your one truck has been entered here. This is a truck. As soon as it entered, and suppose your this way also vehicles are coming, so these vehicles do not have any option of overtaking, right, or passing through this truck. So now if the truck speed is very low, suppose truck is traveling at a speed of suppose VB, and suppose here the speed was VA, and suppose your VA is less than greater than VB, right? And if it is a greater than means you suppose this speed is 60 and this is 20. So now you imagine every vehicles will be stacked here and the queuing also begin to form, right? So in that case, what are the number of shock waves has been created? So the shock wave is the change of traffic state condition. So if there are two different states, so the demarcation is a one shock wave, right? So here, because it is traveling forward or it is moving forward in the forward direction, so there will be queue that will be here. Small vehicles will queued up upstream of this track only, but they will also move. It will not that they will fixed. So it is moving, at least we know it is moving, and moving at which direction? So you see it is not a fixed thing, so it is moving on the forward direction. So it is a forward moving shock wave, but forward forming. Why it is forming? Because the vehicles are queued up, means the congestion scenario is creating. So by propagation of shock wave you are creating the congestions, right? So then this is one shock wave right here, and then immediately here there is another shock wave, because as soon as your truck enters and the forward vehicles are at a certain distance, suppose here, so immediately downstream of this truck, so there is a kind of no flow no density scenario. So there are no vehicles, so that means flow is 0, speed is 0, and the means three flow parameters are 0. So as soon as it is 0, so now a new shock wave has also been created between this B, and if I call it a C, then if call C or D, whatever you can call it, so then between these two, so now there is a second shock wave. And also from this to, because there are some vehicles which are moving, so there will be also a shock wave here, that is called number 3. And as soon as it will remove here, so there will be another 2-3 kinds of shock waves, right? So maybe whenever we will discuss the examples, we will like try to draw a diagram and make you more understand. And if you have any queries, then in that case you can directly ask, right? So then once we know that qualitative and quantitative aspect of shock waves, means the speed is the quantitative aspect, mainly the speed of different shock waves, and the qualitative means is it rear or stationary, right? Is shock wave is changing position or not? Is it forward moving or it is backward moving, right? And is it forming or is it dissipating, right? So those are the 3 scenarios of this qualitative analysis. So now in case of shock wave propagation, so now you know that you can calculate shock wave at each scenario, right? So at each scenario you can calculate what is the speed of the shock wave. But it may not be possible at each time because of the complicacy that individually you need to analyze each flow state and then you need to calculate it, right? So in that case we can use some kind of shock wave propagation theory, so that we can simplify those model and directly we can get the output. So Abhishek, can you just mute yourself because some background noise are coming? Yes, thank you. So now in that scenario, we as a, so last in the last class we as a we actually talked about some kind of models like green shields and Greenberg, those models, right? So as soon as we assume that your traffic flow parameters are assumed to be following the green shield or Greenberg model, right? So these models, if you remember, V and K, density and speed, and this kind of linear model or log linear model, right? So based on that, actually we can use this to calculate what is the speed if there is a small discontinuity between two flow space, and if the stopping condition means if there is a red signal and your suddenly vehicles are stopped, then what is the length of the queue, how to simplify those calculations. So based on that we were using this shock wave propagation theory. And also starting means after the red signal has been over and green signal has been initiated, what is the starting wave, right? So this maybe we will see some examples and then we will try to solve it. So then once your shockwave and that theory concept has been done, so now you need to see the queuing, right? So basics of queuing is, so there is a traffic demand and there is a capacity of a road. So suppose this is a road of width 7 meters, right? So your width is 7 meters. So it has some capacity. Capacity means number of vehicles that will be passing through this particular point per unit time. So suppose number of vehicles passing through the time is 200 vehicles per hour. So it is the capacity. So now suppose your traffic demand is 140 vehicles per hour. So it will easily flow through this particular road. But if it is greater than 200, like 220, so first problem is there will be congestion here, congested unstable situation will be created, and the second point is the some vehicles due to the long queue, because I can give you an example of Bangalore city. If you see the images in the social media, so there are long queues that has been observed, and also sometimes in China also there are some cities where we can see the long queues. So if I know that there are long queues that is happening on that particular stretch of road, even if I want to travel from A to B point, I may not actually travel. I may take some different routes, I may take some different time periods to travel, or I may not at all travel if it is not that necessary, right? So these scenarios, whenever your demand is greater than capacity, so actual demand was something else, but because of the capacity you are following some different paths or different time periods, or you are not traveling, right? So these are called the some potential demands, right? So you may not actually reach or may not actually get. Suppose you want to you observe 200 vehicles at a particular stretch of road, so that is okay, but you cannot say that this is your actual demand, right? Because your capacity is 200 and your vehicle are traveling is 200 only, flowing is 200 only. So there could be those scenarios as well, right? Because of the queuing, people may avoid those time periods as well as those routes. So this is called the queuing, and when queuing can occur, so whenever your capacity is less than demand, so number of vehicles coming are less than your capacity, so there is no chances of queuing, right? So vehicle will pass. But in these scenarios, whenever your demand is greater than capacity, there is a chance that queuing will occur for sure. Right? So then what is queue discharge rate? So if you remember those kind of modern driver curves like that, right? So this QK curve, right? So queue discharge rate is at what rate the queue has been discharging. So suppose let's take an example. In the morning there are light traffic flow, right? And then as soon as the peak period is coming, your vehicle flows is continues to increase, and suppose it is exceeding your capacity, right? So as soon as it exceeds your capacity, so it's an unstable flow. And now suppose after your peak hour is gone, it is also reducing to the first capacity, then the undersaturated situation. So now as your demand is reducing to capacity or less, what will happen that your vehicles, whatever vehicles are queued up, it will try to discharge, right? From the head of the queue, it will try to discharge one by one, one by one, one by one in the backward direction, right? So it is called the queue discharge rate. And sometimes actually what happens, it is actually very closer to capacity, because actually your demand is reached to the capacity, but it is not the actual capacity, because of this transition from unstable to stable, right? So your queue discharge rate is always less than your capacity. So then also there are something called deterministic queuing and stochastic queuing. So actually in real life what happens, your vehicle arrival at a particular intersection or suppose in toll booths, so it is not deterministic, means we cannot say that during 10 to 10:30 there are only 3 vehicles will arrive. We cannot say that. Suppose it is for today maybe 10 to 10:30 three vehicles have arrived, but and the next day it may be 5, at the next other day it may be 2, then the next day it may be 6. So actually it is not a fixed scenario. So if you can plot it, it may be a random distribution kind of anything, any random distribution. It may not be a normal distribution, right? Any random distribution like Poisson distribution, right? So now that is called the stochastic queuing, because your vehicle arrival as well as departure. Suppose you came or arrive at a particular toll and then you are leaving, so that is called the arrival and departure process. So both are not deterministic, mean not fixed, so those are both are changing, so it is called the stochastic queuing. And what is the deterministic queuing? So basically for the purpose of simpler analysis, we are assuming that the queuing process is stochastic, not stochastic, rather deterministic. So then we assume that vehicle arrival is also deterministic. How it is deterministic means it is not a fixed value, but for a particular time period, for say key for 1 hour, it maybe I take the average value as 10. For the next hour maybe I take an average value of 8. For the next hour maybe I take an average value of 12, like that. So it's a kind of deterministic queuing. So why we use deterministic queuing? Although it is not replicating the process, but it helps us to actually approximate some of the things so that we can do other processes rather quickly, because stochastic is very complicated process and uh, it may be sometimes challenging also, right? So now we actually just finished our some kind of refresher of those week 3, whatever has been covered in actual traffic engineering NPTEL course. So now we actually move to the question and answer session. So initially I think there are some theory questions, and then some deterministic queuing numericals as well as some shockwave numericals are also has been designed, right? So as I did in the previous sessions, I will ask the participants about the correct answer, and if they are unable, or if you can give anything, and once you give, then maybe I will discuss them. So let's start. So question 1 is, which of the following statement is false? So which of the statement is false, not true? So total 6 waves are created at a signalized intersection. So forward moving B is false. Okay, backward moving shockwaves. Okay, tell me then, as you quickly give the answer. So uh, in this scenario, whenever demand is equal to the flow in congested region, in this scenario usually what kind of shockwave is created? Tell me, because you are saying this is false. Okay, so what kind of shockwave may be created when the demand is equal to the flow in congested region? And if you want hint, I can stationary. What kind of stationary? Is it frontal stationary or is it rear stationary? If there are, okay, rear stationary, because it is creating at the rear end of the congested region, because already congestion has been already created, and now your demand is goes back to the demand has been reduced, so then the rear stationary shockwave is created. Now tell me, in this scenario, how your rear stationary shockwave will be dissipated? So at what situation it will, so there will not be any rear stationary shockwave. So you can answer by imagining the scenario of that 3-lane road which is meeting a 2-lane bridge. So demand is less than capacity, then your that scenario will be lost, right? Okay, so then we come to the next one. Both frontal and rear stationary shock waves are created when a 3-lane bridge meets a bridge with capacity of 2 lanes. Is it true or is it false? Tell me. When a 3-lane highway meets a bridge with capacity 2 lanes. So is it that both type of shockwave is created? Okay. Now tell me, as you have answered it, that true means both frontal and rear. Now tell me at what scenario there will be a frontal stationary shockwave and what condition there will be a rear stationary shockwave. Is it that both will occur simultaneously or is it something else? So you said demand greater by equal to capacity. Demand is equal to capacity greater rear. Then what about frontal? What about frontal? Congestion will be in the upstream of stop line. Then congestion will be in the upstream of stop line only whenever demand is greater than capacity, not equal. Mostly whenever it will greater than capacity, there will be congestion in the upstream of stop line, right? And a backward moving shock wave is also have been created. And not moving as demand can go beyond 2-lane capacity. No, so you are kind of true, but let me tell you, maybe it will be more clear. So, no wait. So, suppose this is a 3-lane road, and it's meeting this 2-lane bridge. Suppose this is 2-lane and this is 3-lane. So suppose your here your capacity, suppose your demand is 2 lanes demand initially, right? So it will flow because there is a maximum capacity is 2 lane. So there won't be any congestion, but there will be a change of state, right? Why there will be a change of state? Because its capacity is 2 lane, its capacity is 3 lane. So obviously there will be a state change at this point, right? And congestion will occur whenever your demand is greater than 2 lane. Then your backward moving or backward forming shockwave will starts to forming. and it will stay. This forward moving will stay. This stationary, sorry, this stationary, frontal stationary will stay, and then once it is again equal to 2, then your rear stationary will appear here, right, and it will stay up to that time. Demand is equal to 2 length, and once that is over, means demand is less than 2, right. So then your this shock wave will be, your rear stationary will move its position, rear stationary will vanish, and your this shock wave will also be this also be dissipating this congestion region, and this will be there after it will vanish, right. After this shock wave you will be vanish, then it will also vanish, but till that it will be there, this frontal thing. So frontal will start at the initial point, and it will dissipate at the last point, right. It will not dissipate till then. I think it is clear to you, Abhishek. So that's why it will appear both at the last, and then rear will vanish, and then this shock wave will vanish, and then the frontal will vanish, because now your demand is actually very less. As long as your congestion situation will be there at the upstream of that stop line or upstream of that bottleneck point, it will be a stationary shock wave will be present, right. So I think it is clear. So let's move to the next question, right. So which of the following statement is true regarding shock waves? So tell me, first you can answer. Backward moving shock wave will occur when a stream of, you may use your QK diagram, you may plot and try to see that is it stationary shock wave, or is it forward, or is it backward, right. So if this is a QK plot, the shape is this. So now you imagine three scenarios. One scenario will be this, and this will be your shock wave. Another scenario could be this, where this can be the scenario. Another scenario could be this, right. So obviously it is Q and it is K. Now tell me, there are three scenarios. Which of the following statement is true? Tell me. And see, this kind of question will also come in your final exams. So it will be helpful if you do it here. It will boost your confidence, and also the similar type of question usually comes to in the final exams. So you can do it using QK diagram, it will be easy. So this is the stationary scenario. This is stationary, because speed of the shock wave is 0. Q by K is equal to speed of the shock wave, right. So that is 0. You are saying all three are true. Okay. So see, let me just discuss one by one. So here it is saying that stream of higher density and higher flow. So suppose stream of higher density and higher flow, this scenario will meet a stream of lower density. See here, what is this, Q is lower than this Q, right, and this K is lower than this Q. That means the stream of higher density and higher flow meets a stream of lower density and lower flow. Both are low and low and high, the first scenario, and the second, this diagram. Now we are saying that it is the backward moving shock wave, but this is positive, right. The slope is positive only. It is going to this direction means it is positive. So if it is positive means it is forward moving. It is not backward moving. So it is not true. It is false. So did you get it, or should I discuss once again? Because once you got the idea, for rest of that, the same concept will be can be applied. Yes. So now you see, for stationary shock wave, when the two stream of same flow but different density, right? So see the third scenario, the same flow, right? Q is same for this point and this point. Q is same, but the density is different. Suppose K1, K2, whatever it is, right? So then you are saying the stationary shock wave. Yes, it is stationary because the slope is, there is no slope. The horizontal slope means slope is 0, right? So the speed is 0. So it is called the stationary shock wave. So it is true. We know that it is true. Now third one is forward moving shock wave is occur when a stream of higher flow and lower density. So this is higher flow, lower density, and higher flow and lower density, and meets with a flow of lower flow and higher density. This is lower flow and higher density, right? So this is in the negative direction. So it is negative means there should be a backward moving shock wave, not forward. So it is forward. So this is also cross. So our correct answer is B. If we say ABC, then it is the middle one, B, right? Think it is clear? Shall we move to the third one or next one? It is third. It is clear? Okay. So here you are saying that demand starvation can cause hidden bottlenecks. Accept or reject? So what is called demand starvation? Demand starvation means if the capacity of a particular segment doesn't allow the true demand to pass, and hence it is actually causing bottleneck on the next subsequent sections, right? So suppose there is a demand, there is a higher demand, but because of the less capacity of a certain section, it is not allowing the true capacity, true demand to pass, and hence uh, actually you are saying that the less number of vehicles are flowing on the next subsequent 2-3 sections, right? So that is called the demand starvation. So one section is starving the demand of the previous section, right, and creating bottleneck in the third section. So here the answer will be true. So you can refer to the PPT where there is an example of like this on ramp and off ramp. So there were certain volumes like 2800 and then 700 and something is there. So if you remember the section 3, there will be less capacity due to this. You might feel that bottlenecks are there, but actually bottlenecks are on the previous section. So basically it's a true statement that demand starvation can cause hidden bottlenecks, right? So I am not going to discuss because without example it is very difficult to show you that how it is happening. So maybe you can refer directly to the PPTs, right? So you will understand that how it happens. So now tell me, this I have already discussed. So maybe I hope that you will be able to answer. The traffic demand is equal to the observed traffic volume in the absence of congestion. Tell me. So traffic demand is in the absence of congestion. Why it is so? Why it is so? What happens if there is a congestion, your demand is not equal to the observed traffic volume? Means there will be potential demand could be high, but basically people may avoid that particular route due to the heavy congestion, right? And it either it may take different routes, or it may take different time periods, or it might not travel at all, right? So that's what the thing is. So your, in that scenario, your actual traffic demand may not be equal to your observed traffic volume. So why this is important is, suppose you go and collect traffic data, and basically we say that this is the demand of that particular segment, but actually the demand is something else. So suppose why it is necessary, suppose you are you want to improve that particular section, right, where demand is where congestion is high. So now you calculate that, okay, maybe 1400 vehicles are going, it is the current capacity, or based on the observation maybe we find that maybe 1600 vehicles are actually going, and your, or maybe capacity is 1400, so maximum vehicle are coming are, sorry 1400. Now you suppose you want to improve it and improve the capacity by, suppose, some 200 vehicles, or maybe suppose you want to increase the capacity to 2000, right? So now you are expecting that uh, your less congestion and those things will be occurred on those section, but because of the previous hidden demand, right? So now you are seeing that no, the situation remains same, because the hidden demand was 600, suppose, if it is 600 or something 500. So now your scenario doesn't change. So even if you improve your road, or if you widen your road, or you do some kind of traffic management strategies, actually it is not giving you the benefit, right? So then what should be done? So that's why it is needed that you actually calculate the actual traffic demand, right, not the existing observed volume. So in those scenarios it is very helpful. Okay, so now these are the numericals. Okay, this is not from Shockwave but for queuing. So what is the length of the queue? So suppose, so it's an example of the deterministic queuing process, right? So this is the demand rate, it is varying at different time periods, right? It is varying. And then your capacity is this, capacity is fixed, 1500 vehicles per hour, right? It is fixed capacity. So if you remember, in case of deterministic queuing, we have two scenarios. One is your service rate is changing and your demand is constant. Another is your demand is constant, your service rate is changing, right? So suppose in case of signalized intersection, actually your service rate is changing and your demand is fixed, right? If we assume it that the demand is fixed in those scenarios only. So now what we want, to calculate the length of the queue dissipated at 3.5 hours. So what is the number of, at this point, what is the number of vehicles? So suppose your demand is 1200 vehicles and your capacity is 1500 vehicles. So is there any queue that can be developed? No, because your capacity is higher, so there won't be any queue, so vehicles will pass, right? So up to this point, 1500 and 1500 matching, so there won't be any queue. So as soon as it is crosses, your demand crosses 1500, it will start, your queue will be started, right? Your queue generation will be started, and up to this point your queue will be generated. Now after that your queue dissipation will start, right? Because your already demand is lower than your capacity. So now there will be, after some time period, that every queue will be dissipated. Whatever the vehicles are there, vehicle volume in terms of queue, that will be dissipated. But that we are not going to calculate here. But what rather we are calculating is the up to this, from this point, from the, or up to this, what is the length of queue that can be dissipated, right? So you may want to calculate it. I do not want to do it directly, so maybe I will wait for some time so that you can calculate, right? So you calculate. It is not difficult. So either you can use the formula that is given in the PPT, or else also it is told that even by using graphical method or triangle, using the triangles, you can solve it actually, right? So tell me what is the length of the queue. I will wait for some time. And this is very important because there could be different things that can come in your exam from this part only. So because this is a very important question, so you may also get couple of similar type of questions in your final exams as well, right? So it is a very important topic, so do it, it will benefit you. So I am waiting. I hope that you are trying. Also, I am speaking at a lower voice because I am having some throat issues today. Oh, what are you doing? You can reply me by saying the yes, I am doing it. Okay, I will wait. You all can try actually. So, first you need to calculate at what time demand is equal to the capacity, right? So, at what time demand is equal to the capacity, that you have to calculate. Once it is done, I think rest is very easy, right? So, suppose for 2.5, at 2.5 this time, we know that our demand is 1800, right? Our demand is 1800. 2.5. Now at 3.5, what is the demand? So your demand is this 1000. So now what I want to know that at 1500 demand, whenever, because 1500 is the capacity, at that demand 1500, what is the time? That's the first thing. What is the time? So if you know the linear interpolation, you can do a linear interpolation here. Otherwise, what you can do simply, because it is 1800 and it is reduced to 800, means your 1800 minus 1000 is 800, reduces 800 vehicles per hour. That demand reduces at 1 hour, because 3.5 minus 1.5, right, 1 hour. So now you want to reduce it from 1800 to 1500. So now you want to know that if the reduction is 300, so then it is taking how much time from 2.5. Obviously, like from 2.5, if I plus 1, then it is called 3.5, right? So then it is nothing but a simple thing, 1 by 800 into 300. So 3 by 8. So 2.5 plus 3 by 8. So this is the time at which your demand is equal to capacity. So what is 3 by 8 if you calculate? So 3 by 8 is 0.375. So then 2.5 plus 0.375. So it is coming out as 2.875. So this is the time, and it is logical, right? Because it is 2.5 and 3.5, and it is somewhere in this middle situation, 2.875, right? So now I know. So what I want to know, I want to know that at 3.5 what is the Q dissipation. So you may imagine this is your triangle, right? Dissipation triangle. So now your this value is how much? This is 1000, this is 1500, this is 500 only. And your this value is how much? 2.875, 3.5, right? Means 3.5 minus 2.875. So what is the area under this curve, right? Under this two curve at this point and this point, it is called the number of, it is equal to the number of vehicles that have been dissipated, or queued vehicles, right? How many numbers has been dissipated. So it is what? Half into 500 means 250, right? Half into perpendicular into base, right? Half into 500 means 250. 250 into this 3.5 minus 2.875. So 3.5 minus 2.875 is 6.625 into 250. So it will come out to be the 156.25. Or we can say that 156 vehicles or something, because there is no logic in writing to 156.25, right? But okay, you can write it. So now did you understand, or like you are calculating, so is it that your value and my value is same or no? Got same. So did you do this or do something you did in a different way? So what I discussed, is it the same or you did something else to calculate the same? Okay. So once you did this, now you tell me, because that I won't calculate. Here you tell me. The same diagram you can use, right? The same this diagram. So you calculate the size of the queue developing during the period whenever demand is greater than capacity. You tell me. This answer I won't do it, you will do it. When demand is greater than capacity, what is the size of the queue? Calculate it. What is the size of queue? Obviously, whenever your demand is greater than your capacity, then only Q will occurs, right? And whenever your demand is 394, okay. Let us come here and erase it, and then we shall see what is the answer. You said 394. Let me check also. Okay. So, of into what is this? This we need to calculate. So here it is 1200 and here it is 1800. So 600 is increasing at a time of 0.5 hours, right? So now we want to increase 300. So 0.5 by 100 into 3 means half. So 0.5 by 2, I think, right? So 0.5 so 0.25 and 1.25, because this is 1 and 12 and 18 is 600 and it is 1.5 means 0.5 and it is 12 to 15 means 3 only, okay, half 1.25, right? And this was came out to be okay. What was this value? 3 point, I forgot, I need to calculate again. So 2.1800 minus 1000 means 800. 2.875, okay. 2.875 and this is 300. So 2.875 minus 1.25 is 1.625 is this 1.625 and this is 1. So 1 plus 1.625 means 2.625. So 2.625 into 300 by 2. 393.75 means 394. Okay. So you are right. It will be just in this area, right? It's a trapezoid, so it's a trapezoidal area. Either you can do a trapezoid directly. The formula is half into this parallel x, whatever the parallel is, you can sum it and then into the height of this, right? Other thing what you can do, you can take two triangles and one rectangle. That area is the number of cube. Okay, now do it. So you see, so this is the arrival curve and this is the departure curve. It's a signalized intersection, right? So it is the red, 30 seconds is red, and then vehicles are dispatching at a particular dispatch rate, and then your arrival and departure is equal, and then again your rate, and then again it is red and green like this, right? So on a single lane approach to a signalized intersection, the effective green and effective red is 30 seconds each, right? So there is nothing short of yellow interval here. It is effective everything. So the arrival rate of vehicles is, arrival rate is 360. So per hour 360 vehicles are arriving. So this is the arrival. And your saturation flow rate, saturation means after your signal turns green, the saturation rate is 1440 vehicles per hour per green time, because vehicles will be departing only at the green time. So your saturation flow is given in terms of per hour per green time, right? So assume that your t equal to 0 and the signal has just turned red here. Here it is signal turned red. And then they calculate the average delay for the arrival vehicles within one complete cycle. So suppose this is 30 and this is one complete cycle, because this is again red. So here it is red, it is green, and then red, and then green, and so on, right? So one complete cycle means, suppose this is up to this, maybe you want to take one complete cycle, it is saying. So how to calculate the average delay? So let me also give you some hint. So suppose here, see, the vehicle is, the signal has turned red. So even if your signal is turned red, so vehicle will arrive, right? These are the vehicle arrival curve. So it will arrive, but it will stay and it will face some delay. Here first vehicle maybe faces delay of 30 seconds, second vehicle some less delay, third vehicle, and so on and so forth. And here what happens, your your arrival and vehicle rate is equal means, so there are no vehicles which is queued due to the signal. Everything has been going, whatever coming it goes, whatever comes it is good, it is not staying as in the form of queue. And then it is going for some time, and then again it is coming red, and then there will be queue. So what is queue? Queue is this, vertical line is queue and horizontal line is delay. So if you can calculate the area of this triangle, you may get the total delay, cumulative delay, right? Cumulative vehicles, what is the cumulative delay that you can get here. So can you calculate what is the average delay in this scenario? This is also very important problem, although it is not directly given in the PPT, but you may expect it either in the assignments or in the final exams, because it is also like your demand is kind of same, arrival rate is same, but your service is changing, right? Your service rate means your actual departure rate is changing. So let me wait for some time. You first try to do it, maybe then I will do it. So, are you trying? Okay, do it. So, the hint is this is unknown. Number of vehicles, cumulative number of vehicles arrived at that point. This point has to be calculated. This is unknown. We know this is 30, but this is unknown. So, y axis is unknown. So, are you are you doing it? Is it you are able to do it? So did you calculate something? Okay, let me discuss then. See, already I told that uh, first vehicle may face delay of 30, second vehicle is suppose 29, 28 and so on, and this vehicle will face no delay, right? Because your arrival and departure rate is same, that means it is going at that rate, so there will be no delay, right, for this point. So till that point to this point, so this area of the triangle we need to calculate. So we know that your x is 30, your horizontal base is, but we don't know how many cumulative number of vehicle is there. But we know for sure that at that particular point your arrival rate means the number of vehicles that arrived equal to the number of vehicles that depart, right? So whatever the number of vehicle came, it is departed. So there are no vehicles, no queuing, no delay, right? It is understood, I think it is clear. So based on this criteria, so what is your arrival rate? Your arrival rate is 360, right? So suppose your this point is T, right? So now your arrival rate is 360 into T. And what is your departure rate? Departure rate is 1440 into what is the green time, right? After 30, what is the green time? Suppose this is T. So T minus 30 will be the green time. 30 is the red time, right? Because your vehicle will depart only during green time, not during red, for obvious reasons, right? And for arrival, it will come irrespective of your green time and red time. It will come because vehicle are coming, so it will come, right? So this is the considering it is an isolated intersection, right? It is an isolated intersection, obviously. So for this 360 into T, so 360 into total T time is equal to 1440 into T minus 30, right? So now we need to calculate what is the T. So what will be the T? 1440 minus 360, right? Let me calculate from here what is the T. So 1440 minus 360 equal to 1080. 1080. So see, your value of T will be 40 seconds. 40 seconds. So because these are vehicle per hour, but even if I divided it by 3600 to make it seconds, so because it will also be divided by the same thing, so it will cut, right? So it will be a 40 seconds. So 40 seconds is your T. So now how many number of vehicles that have arrived at 40 seconds? So it will be 360 is the vehicle arrival rate, number of vehicles per hour, into 40 seconds, but it is in the hour, so by 3600. So now see, this is the 4 number of vehicles. It is the 4 number of vehicles that have come at 40 seconds and leave at 10 seconds because the green time is 10, right? So now your total delay is what? Total delay is half of the triangle, 4 into 30. 30 is the total delay, right? So it is comes out to be 60. Total delay is 60 seconds. Now what we want is not the total delay, we want the average delay for the arriving vehicles within one complete cycle. So see, one complete cycle is up to this, up to 60, because 30 is your green time and 30 is your red time. So 60 seconds, what is the number of vehicles that have arrived? Is the 360 by 3600 means 10 into 60 means 6 vehicles, right? 6 vehicle will arrive during 60 seconds. So then your total delay by your total arrived vehicles is 60 by 6 is 10 seconds. So it is the average delay per cycle, one complete cycle or initial complete cycle, right? So did you understand the problem or is there any difficulty? You can ask. So why we take half into 4 into 30, why not 40, is that up to 30 only, that portion, due to that portion only vehicle will incur delay. After that vehicle won't incur any delay, right? But your axis will be 4. So it is the horizontal projection of the triangle that will give you the delay, right? Horizontal projection of the triangle. Tell me, did you understand the problem or okay? See, delay will occur up to how much? So let me remove this, just erase this part. So see, first vehicle will come and face suppose 30 seconds, next vehicle maybe 29 and so on and so forth, right, up to this point, right? So now at this point, which is comes out to be 40 seconds, your arrival rate and departure rate is equal, means your arrival rate and capacity is equal. So what do you, so there will be no queue, right? So there will be no delay. This is, you are getting this point, that if your arrival rate and departure rate is equal, means if 5 vehicles are coming and 5 vehicles are leaving, so is there will be delay due to that particular signal or something? No, right? So at that portion to this portion there will be no delay. So delay will be occurring at this portion only, which is comes out to be 60 second. 60 second is one delay or cumulative delay. So if you see the curve is cumulative arrival or departure curve. Cumulative means one, suppose at one instance one vehicle came, second instance one vehicle came, so it will just add up 1 2 3 4 5, cumulative, CDF, cumulative distribution function curve, right? So if it is a cumulative curve, right, so then your total delay is for this section and this is 60 second, right? But how many numbers, so here what they said, that average delay for the arriving vehicles, for the arriving vehicles. But even if these vehicles have not arrived and not facing direct delays, but for that cycle, what is the average? So suppose at a particular cycle, 2 vehicles are facing delay of 30 seconds or 2 vehicles are 0 seconds. What is the average? 2 into 30 plus 2 into 0 by 4. Is it not the average? Two vehicles facing delay of 30 seconds. 2 into 30, 60 total delay. And another two vehicles at that particular cycle are facing no delay. But for that particular cycle, what is the average delay? 2 into 30 plus 2 into 0 by 2 plus 2. There are 4 vehicles. Okay. Okay. So this is what this problem is. So I think that's come to an end of my problem answer session. So maybe if you have any queries or questions regarding week 3, you may ask, and if not, then maybe we will wrap up this. Tell me if you want to know something, or if there are any doubts regarding anything. No? Okay, thank you. Then we are just closing this for today. Next week we will meet on the same time, right? For the week 4, right? So thank you. I am closing it.